Happy everyone.
Afternoon. Have your exams graded. Your midterm is based on the closed notes portion of the exam. Okay. And but it turns out, interestingly enough, Westerberg
Would be over here.
he would be over there if he was here.
Yeah.
Emma Daly. In this case, sorry. Max. Evans. Would he be here if you were here?
They're not still fine or something. I don't care.
Will Focus. That was a little too quick, sorry. Stephen. Also named that. Dominic. Corey Pfeiffer, are you? Joe Rice. Joshua. Nope, sorry. Keaton Rowe, so it is. Keaton. Okay. Wesley. Adam Shearer. Edgar.
Over here.
That makes sense. Dale.
I have some sense that's really concerning. Also, I can't read that.
Your name's on the hallway.
Yeah.
Isaac Withers. Would he be here too? No. Ben. Yeah, I know. Am I missing your exam?
Oh, thank you.
Did you take it?
I did take it.
Oh, okay, I didn't get back to you. Okay.
Nice.
You may have not got the right grade.
Yeah.
Okay. We'll work through that.
Okay.
That was funny.
Thank you.
I'm actually surprised. I'm surprised, Jay. Is that you?
Yeah.
Yeah.
This is my name.
This is the open notes portion. And this was not part of your midterms. What you got is a grade on the top, and an A, B, C, D, or F on the, next to the grade is the grade you got at midterm.
Okay.
It's based solely on the closed notes portion of the exam. So I find interesting that I've not seen this before, but students who did really well on the closed notes portion typically did much poorer on the open notes portion.
Really?
Yes, I don't know why. But I have suspicion.
No, that's so weird.
Totally had seen it before.
Yeah.
Thank you, sorry, my head. Not universal. Dominic?
Yeah. Where all these out of?
Talk about that later. No. Ian Evans. Can you be here?
My brain wasn't doing it, so I had like. So I think that.
Which is, you know, typical.
I thought we would walk through this.
She's better than I thought. Okay.
Leslie Burke.
Not here.
Okay. Let's walk through this. These are the general rules, right? You are welcome to argue for points, you just can't do it today. Okay, why not today? Why not today? Because that's the rule. It's not complicated. Besides, I want you to look it over. You know, you get all hot and bothered about your grade, you come in hot, and I'd rather you think about it and come back and argue with me. You might be surprised, but I'm all about the argument. So, good?
Okay.
Okay. A couple problem areas that we will address. First one was a gimme. How many points make a line? 3. Good. Good start. 5 factors that control suspension biology. If you didn't think that was going to be on here, you were not paying attention. You're going to see it again, too. We have at least one more exam, possibly 2. It might show up on both of those. You may leave here, and 20 years from now, the only thing you remember from this class is the 5 factors that control suspension biology. I've done my job. Why are measured particle size, surface, or measured surface area always greater than calculated? Calculus assumes a spherical particle is spherical. You can get into some sort of nonsense about surface roughness. Don't care. Okay. So that's the answer. Particles are not perfectly spherical. I answer my own questions. For a spherical alumina powder, right away, spherical, so you're going to calculate it, right? 6 over rho times d should be 6 divided by 4 times 9.6. You had a homework assignment, right, where you were supposed to demonstrate that the units work. And that the surface area will come out, the surface area and density in grams per cubic centimeter, you get back microns. So you should get 0.156 microns or something close to that. Okay, if you round it up to 0.16, I don't care. You came back with something that was grossly wrong, and I marked it wrong. You came back with 15.6, you got it wrong. Okay, that's 156 nanometers. In the future, I might tell you what the units are I want answered in, but that should be it. Okay, PET method, measuring surface area, corrects for multi-layer coverage of nitrogen on the particle surface. That's the construction with the linear regression part of it. Powder produced by combination of grinding technique gives a log-normal particle size distribution. The thing here is that we can argue about that because we did talk a little bit about something that's giving you Weibull distributions. But the fact is, it can't give you normal. You can't. We haven't talked about this idea of initial flaw population, because I'm not sure that it actually works. We didn't talk about it in here. And monodispersive spherical powder. Come on, you're crushing these things, right? Okay. First curve page is worth 30. In the math, I think the total is 135 or something. Okay. Froth flotation is commonly used to exploit, I guess I should have grammatically changed that to exploit photochemistry differences between mineral species. Okay? So, what are you doing? What's froth flotation doing? It doesn't separate minerals by different density, right? That's dense media separation. It's not a preferred route or beneficiation. You can get away with doing something cheaper, you're going to do that, so it's not preferred. It's common, but it's not the preferred route. You could argue that it actually exploits not photochemistry differences, but differences in hydrophobic character of the nature of the particle. Don't care. This is the right answer. It's not a substitution for the Bayer process because there is no substitution for the Bayer process. Given a spherical powder, somebody asked me under exam, they saw this question 3 times. It's like maybe the question isn't exactly the same each time, but nonetheless, yes. Yeah. Spherical powder, what you have is surface area is equivalent, so rho of A times D of A is equal to rho of Z times D of Z. And you are,
That's 0.
okay, then. Okay, so when you do that, since the density of aluminum is less than the density of zirconia, then the size of the aluminum must be bigger. It says, which would have a larger particle size, it has to be the aluminum. My exams, the 4th answer here, Not enough information to answer the question is almost never the answer. By the way, in case you're wondering. Cracking and warping are most likely due to uneven packing particles in the forming stage. What is likely the most important factor that determines the cost of ceramic raw material? We didn't really talk about this, did we? Doesn't make a difference, you can figure it out, right? Number of process steps. That encompasses everything. It encompasses particle size, distribution, purity, quality of the ore, agglomeration of powder. It's all invested in that one. Okay, this one here, lot 2 materials. So I did it on the take-home portion. It looks the same. It's the same question, more or less. Okay, that's what it should look like. So on the left, for A, 300 divided by 400,000, so 300 megapascals divided by 400 gigapascals is 0.000075, and 75 divided by 72,000 is 0.001. So you can set this up 50, 100, 150, 200, 250, 300 on the y-axis, that's your stress, and then 0.00025 to 0.001, and then these are your 2 lines. They are straight lines, correct? Why? Because they behave as elastic solids. The failure is brittle, right? If you have a linear stress-strain relationship in an elastic solid. Okay. No, I didn't ask you that question. They are straight lines. Okay? Metals are not straight lines. You don't care for metals. I'm sorry, you don't deal with metals. Good? Good? So that means B has a greater failure strain. We'll come back to this question in a few minutes. No, how would your answer change if the finite strain elastic modulus values were provided? We don't have to come back to that. If your strain and failure was the same, it doesn't change, correct? But if you are calculating your strain and failure from elastic modulus, then your calculated strain and failure would be much greater. Good? Because you would have a lower elastic modulus than this value, and you would go to the same stress level. So we do it for the top one is easiest. So you would have this strain versus stress, and here's our first case, right, for failure. But our stress level stays the same. So if I reduce my elastic modulus, my strain and failure increases dramatically. So this is elastic modulus finite versus elastic modulus from zero strain. Good? I'm pretty lenient on that one, and your opportunity, of course, is to argue for points. You don't like what I said. Page 3. Particle, I did the short version. I need answers because as low grade these exams. Particle packing decreases when the particle size falls below the flow size limit. What is the typical particle size associated with flow size limit? Which I neglected to answer, therefore I lost 2 points. And why does pack efficiency decrease when particles are smaller than this limit? The answer is roughly 30 microns. Close. If you told me the 30 nanometers, you only missed it by a factor of 1,000, and therefore it was wrong. Okay. If you told me that it was 10 microns, I probably accepted that. And then Van der Waals attraction forces is why the particles agglomerate, they dominate over gravity, something to that effect. Good. Next one is interesting. Identify the components and calculate the percentage of the components in the blended powder. Those, of course, the has a measured specific surface area of 4.85 and a density of 3.05. There's 2 ways to do this, obviously. Perhaps obviously. Where do my calculations? Should get something like this. Mass basis, which you get from surface area, is 58% quartz, 42% aluminum. Good? Okay. Yes?
That was that's the number.
There's a bunch of 12s, a couple 11s. I don't know. We're just going to take them in order.
Right.
So we're on this one. The 11, number 11 that comes after number 12. Good. Have you done numbered lists in Word?
Yeah.
I can't figure it out. Goes along fine, and then it says, you know, I had to copy and paste the question, it says, continue number, I say yes, and nothing happens. So then I change the number, and then all the numbers change below that, but then the ones above that had insert questions. I don't know. Like the person who did graphics did numbered lists in Microsoft. So that's 30% quartz and 70% aluminum on a volume basis. Good. So, did you get something like that? So on the open notes portion, this is a bit baffling, but I'd never done the question this way before, and I asked you to calculate what the density of the surface area was, and some of you didn't quite get that. You don't quite understand that. Number 12. Okay, let me rephrase that. Second, number 12, okay, which is give me two ways to determine determine the particle's log normal particle size distribution. There are two ways, but what should happen is if you answered the question, you did not get points off. Do you understand? In other words, you had to buy. If you didn't answer the question, then you got it wrong. Do you understand? If you attempted an answer, I give you credit for it. If you decided not to answer the question and skipped it, then you got it wrong. This isn't like the SAT score where you make an attempt at an answer and you lose part of the points if you get it wrong. You know, if you get it wrong, you lose all the points, right? If you guess at the question, you know, I don't care. But I wanted you to, you know, you should guess at the question. There's two ways to do this. Linear relationship of probability versus log of particle size would be one. The other is that the surface area D50 is equivalent to the summation of surface area over the entire particle size distribution. That's the second one. If you recall, we talked about that in class, where if you take a normal distribution of particles and you measure the surface area, so if you have this basically on a Gaussian distribution, frequency, log particle size, right, and you take the D50 and you were to do this sort of histogram approach and calculate the weighted average and the summation of all the surface areas of all the particles, it turns out that that summation is equivalent to the surface area calculated with the D50 for a log normal distribution. So that's what the answer was. But I felt that the question was unfair because we really haven't talked about it that much. If you want to argue with me that's fair, then I'm okay with that.
If it's fair, I answered it at that point.
But you didn't get points off.
It's true.
Does this make sense? Number 13. I think it's the only number 13, by the way. Derive. If you just wrote down what I wrote down here, then you didn't get credit for the question, right? You have to derive. So you start with volume is 4/3 pi r cubed, area is 4 pi r squared, and then you do the math. Okay? That's what I asked you to do. And then identify units, which would have helped you other places. Here's the second time you see this question. Given a spherical powder, which would have a smaller particle size. Well, it's not the same question. Okay? So, and that would be zirconium. What's another way to ask the question? Two particles of the same size which have a higher surface area, you can do it that way too. Particle size distribution unknown power demonstrates two straight lines of cubic mass divided then plotted on probability axis as function of log particle size, is like an indication of two powders mixed together. If you recall, the second answer here, mixture of dispersed and agglomerated, the agglomerated powders don't have a log normal distribution normally. So they don't behave in the same way. You don't get two straight lines. You get a straight line and a curve with an agglomerated powder. Incomplete milling process, they don't know what that means. Colloidal fracture of the particles. Argument. (16) Top on page 4. Apparent viscosity is the calculated viscosity for a shear special rate data pair. Isotropic suspension is typically observed for shaped particles that align during shearing. Using a helium pycnometer to measure density of a sintered sample does not work because only the skeletal density is measured. And what you're trying to do is figure out how far you are along that sintering process, okay, and you need the open porosity to get that information, and you can't get open porosity from a helium pycnometer. It doesn't measure the closed porosity unless you have other information. It It does ignore the open porosity, but that doesn't make it an ideal technique. And we don't care that the gas is stagnant, that's not really true. Okay. 19, plot of strength as a functional elastic modulus, right, indicates that the flaw size is dictated by the process. Because what you're seeing is that the strength scales linearly with elastic modulus. And when that is the case, okay, and we have a relationship that E is a function, excuse me, wrong way. Gamma is a function of E, right? So this becomes sigma is equal to E times square root of 2B over pi. C, this is your critical flaw size. So it says that if this scales linearly, the slope of this line is your strain of failure, but also indicates the flaw population. And that indicates that the flaws are constant. That means they're dictated by the process. The spherical particles, decreasing particle size decreases number of particles by a factor of 10 to the third, 10 to the 3. Okay, so what you get is because volume scales with the cube of radius, so when the size gets smaller, the number of particles goes up. The spherical particles decrease in particle size by 10x. It's linear with size. So it increases the surface area by a factor of 10. Number 22 created a lot of trouble for a lot of people. Okay. Why is that? Why froth flotation? Why not? Why is it that froth flotation does not work for the processing of the beneficiation of aluminum or bauxite?
Does the same stuff for the rest of the stuff?
No. Did you hear what he said? He did this thing with his hand. He said the aluminum does similar chemistry. What he meant to say was that similar surface chemistry to the iron ore and iron ore. That's not the case. What is it that limits and forces us to use the Baer process? Because if you could do froth flotation on bauxite, you would do froth flotation on bauxite. The Baer process is probably the most expensive mineral beneficiation process on the planet. It's expensive. There's got to be a justification. What is it that forces us to use the Baer process to make aluminum? You want to read your answer? I don't remember what you had. Say, well, I don't care if it's right. No, maybe not.
I said the bauxite does not break apart in water, so that is why more expensive process needs to be used.
Did you get any credit?
Maybe.
Dante?
Maybe I did.
Maybe you didn't. Can't tell my grades.
I'll read yours then. Alumina requires the Baer process to be chemically removed from bauxite and precipitated out, not separately using froth flotation.
Which is exactly just a rewording of the question rather than an answer to the question. While I appreciate the approach, I actually read the answers. The problem is that the microstructure of the ore is too fine. You cannot mechanically separate, right, aluminum hydroxide from iron. Iron oxide or hydroxide, right?
The answer is you give up on what?
Microstructure. Yes.
So it needs to be chemically separated.
It can only be chemically
So
separated.
when I said the Baer process, it requires chemical separation from the bauxite to be reprecipitated.
But it doesn't-
Not
And
available.
why? Why?
Well, I mean,
Why? Because you just wanted to do it that way? No, you didn't tell me what the problem is. You just told me what the solution is. And
Because it can't be extracted via only colloidal surface chemistry, how does that, like, why does that not?
you can also extract other, you can beneficiate other things by using a chemical route. You just prefer not to. The problem with froth flotation is you need to be able to break apart that ore into individual species that can be treated. And when that ore is intimately mixed together in a fine-grained structure, when you crush it, you don't actually crush it and liberate, say, aluminum hydroxide particles, which is not what you said. But you can argue about it tomorrow, or whatever day. I have a couple of microstructures that are worthwhile looking at the moment. Here. So one of the things that you should remember, right, is that everything is driven by cost. Right? The ore at the top can be crushed, and you liberate these chromite and olivine particles from each other. The one at the bottom, you're going to have difficulty doing that. There's a size bar here. It says it's 178 microns, which is interesting, and I assume they're both the same. There's 100 microns in the upper corner. But the problem is that because that microstructure is so fine, when you fracture those particles, fracture that ore, you're not going to be able to break that out into discrete particles that can be separated. That's actually the foundation or the need, or what drives the ability to do frost flotation, is that you can crush that ore into particles which are essentially one component rather than multiple components. And you can't do that with bauxite. This one has the potential to do so. You get 100 micron getting the particles out. They're also mixed with pyrite. May or may not work. This one definitely would work. You can break it up into pieces. This one you could do. This one you can do. This one you can't. Okay, as that ore becomes more and more complex and intercalated, if you will, or mixed together, you can't separate it by frost flotation, and that's a hallmark of bauxite. Okay, if someone would like extra credit in here, you get some bauxite chunks and you can polish them and look at the microstructures. Awesome.
Where do you find bauxite?
You're gonna ask me for it. Not to be like, duh, but I said, we have bauxite. Do just about everything. Fair enough? Ask me for it. Good? Two fluids of the same viscosity, shear rate of one fluid possesses independent behavior, the other has pseudoplastic behavior, which would appear to be lower viscosity than maple. Typical shear rates are 10 to 1,000, so the pseudoplastic fluids appear to have a lower viscosity. Good? Okay? Oh, look to this side. Oh, there's that question again. However, right? Doesn't mean that everybody got it right, because you have to read before I open it. Okay. There's a question about frost flotation again. Okay. Let me open those portions. And then this side here, the common to assign cracking work to drying required stages in the manufacturing process. What's the root cause? Cracking work are the result of non-uniform particle packing during the forming process. Variable density shrink more, you get some attention. High density and compression is sufficient strain, you get cracking. If not sufficient strain, you get warping. Okay. This question here, number 6. Identify the components and copy specific surface density of 38% alumina, 78% quartz, have the properties in the table. So it's very straightforward. 0.3, since you do surface area on a mass basis, 0.3 times 9.6 plus 0.7 times 1.5 gives you 3.93 meters per gram. And then to do density, it has to be 1 over the density times fraction, mass fraction times 1 over the density plus the mass fraction times 1 over the density. That works out to 0.339. 1 over 0.339 is 2.95. So I hadn't approached it that way before. That was good. Number 7, you have probably room to argue if you feel so inclined. All right. It says private justification that demonstrates particle size distribution provides log normal. In fact, it is not. So you could argue that I misled you. However, I have a question for you all. Okay, and I would say that roughly half of you got a curve to this line and told me it was a line, a straight line. Okay, now I gotta like take some issue with that. Okay, and if it's a straight line, then you can say it's a straight line. If it's not a straight line, then you gotta say it's not a straight line. Just because you want it to be a straight line is a justification for calling it a straight line. So what you would argue is that you had actually 2 particle types mixed within this sample. Nobody did this, but you could say that 80% of my particles roughly are one type, and I've got 20% of something else that would be true from the plot, right? But the bottom line is, right, that this is not a straight line. Okay? No matter how much you want it to be a straight line, it's not a straight line. You could also come back and say, it was a curve, and you could argue for this to be a curve, although this is pretty good here for straight. This is not bad for straight either, but you could argue for a curve and say, in fact, it's not a log normal distribution. Okay? So I can reword the question to make it better. So it's a trick question. It was not intentional. It's got the wrong data set. I have a lot of data sets. And
Why is this a trick question?
because it's not a straight line, it's not log normal. So, good?
Oh, so it's not supposed to be.
No, you just gotta look at the data after you plot it and decide what it is, and that was the example. Any questions? How does it break down? The way that it works is, the second part was worth 50 points, total 30 points on the first page, 20 on the second. 135 on the closed notes portion. I don't weight them differently. They are just straight up, so the open notes portion was worth less than the other overall. Okay. I did not have the open notes portion graded in time to submit your grades, but I did get your grades on time. Just for the closed notes portion, it turns out that it would have affected some of you a little bit. You would have went up or down between A and B. Those of you who had C's or lower didn't make any difference. Okay. However, this is the takeaway, right? This has been semestered. Although statistically, and I'm going to go back someday when I have a bunch of free time and look over 25 years of grades and demonstrate that the grade you get at midterm is often exactly the grade you get at the final. But it doesn't have to be that way. Good? It can go either way. You have the opportunity to screw this up and get a 4 grade, or the opportunity to raise your grade. Good? Okay? That means that if you have an A, I would not post. So I anticipate 2 more exams in here. One will be a second midterm, and the other will be the final exam. Okay? That will constitute your grade, plus you have the project that you're working on. Good? Okay? We have another issue that I want to bring up. I want you to think about it. We will talk about it next time we meet, which is Friday, right?
Yes.
The last week of class and the week of Thanksgiving, I will very likely be out of town because of a conference in China. So what I would like to do is get ahead of that, and you would have that week off. Would be acceptable? Would that be acceptable to everybody? That you not have to meet in this class for the last week of class? Okay. What does that require? It requires that we will find times to have extra lectures. Maybe for the next few weeks, we might start not this week, but next week, maybe on Thursday or something like that. We can meet for an hour and get our lectures out of the way. I don't care what day of the week it is. That's why I'm telling you now that it has to be one day a week. I would tape the lectures so you have that. We'll get out ahead of it so that we will be done with this class except for a review and the final before Thanksgiving. Are you all right with that? Everybody all right with that? Okay. So then you'll have Thanksgiving week off, and you'll have the week after that off, with the exception of probably the Friday of that week. We'll meet for review in advance of the final. Is that good? Okay, if that works, let's put that in place. But you have to decide, I do not care what day of the week, and I think it's best if we do it in the evening, but we can talk about it, find another time during the day, I don't care. Okay, it's up to you. Good? And I am taping the lectures, so you have that as a resource also. Any questions? Okay, so I'd like to come up with a schedule on Friday. That would be my homework, and I would put together a schedule when I know that I will be out, when I anticipate being out. The Chinese are a little strange. They changed the dates of the conference. It's supposed to be the week of Thanksgiving, and now it's the week after that, and it's complicated. We're trying to develop a relationship with an institution there. That's why I'm going, actually, other than to give a talk. So,
I think I misheard you, that's all.
can't imagine. Let's not go there and find out what it was. Okay, so here's where we are. Let's go here. The way I see it is we have completed electrostatic stabilization. Everybody good with that? On the last day of class, before the mid-semester break, when half of you had something better to do, we went through and looked at the decay functions associated with the double layer. That would be this, okay? And I will post the in-class assignment online so you can take a look at it, okay? In other words, how does the electrical potential decay change with the change in pH, change in nurse potential, or a change in ionic strength? We walked through that in class last Friday, okay? So, in my opinion, that wraps up electrostatic stabilization with this exception, right? We have these two plots. The one on the right is zeta potential, lower right is zeta potential. The one on the left is viscosity. And we haven't really looked at this very carefully or extensively, okay? I gave a talk on corrosion of alumina at the MS&T conference in Portland, Oregon. This one looks like it. Yeah. Okay. So here's what we have: solubility of aluminum in water, blah blah blah. All right. This is the deal. If I look at this effective pH, right, on zeta, or effective pH on zeta potential. Okay, the x-axis is pH, the y-axis is zeta potential. These are measured values. In the lower left-hand corner, you see that this is 5 volume percent, APA 0.5, which is called an average purity alumina. It's actually a high purity alumina. They're over called HPA, which is much higher purity. But essentially, it's an alpha alumina particle. Okay, very well behaved, obtained, not obtained through the Baer process, but that's not important to you. And then the surface area is 7.8 meters squared per gram. This last thing you'll see here says a 10 millimolar potassium chloride background electrolyte. Okay, so what we do is when we measure zeta potential, you do it in the presence of a background electrolyte. So what that means is that you actually have ions potentially added that would be considered an indifferent electrolyte. So potassium chloride fits that bill. So does potassium nitrate. And technically, it would have been better to have used potassium nitrate. Okay? It's not important. What happens then is that with that background electrolyte, if I add, say, hydrochloric acid, the chlorine concentration does not change significantly because I'm against that background electrolyte. And that is the way the zeta potential should be measured. And so we did it properly in that respect. If I add sodium hydroxide, and the sodium ion that comes in with the NaOH does not significantly change the overall ion strength, because what will happen is that if you bring in HCl, for example, it turns out that HCl is not an indifferent electrolyte. Not only is it a pH determining ion with the H, but the chlorine is not inert in that situation because you don't have a cation to convert to. So you use a background electrolyte. Just so that's a point of information. What we see is about the isoelectric point here, okay, which is right about 9. You would argue that if I go up in pH or if I go down in pH, that the slope of that zeta potential curve is the same. You agree? Okay. So, what did that imply? Let me change the question. Let me fill in the question a little more. What would that imply in terms of the rheology response of this suspension?
It's a different,
Say again?
it behaves the same way when.
Either way, you would expect the viscosity to drop as you move away from the isoelectric point, regardless of direction. Does that make sense? So if you push the pH up, you would expect the viscosity to decrease at the same rate that you would see the viscosity decrease if you push the pH down. Okay, now, there's 4 sets of data here. Let's start with ammonium hydroxide and sodium hydroxide in the lower right. What do you see about that? They behave similarly? Good? Okay, they are on top of each other for the most part, right? They're exactly the same. Now, HCl, okay, apparently behaves similarly but oppositely to ammonium hydroxide or sodium hydroxide. The sulfuric acid behaves differently, okay? And what it does is the zeta potential goes up a little bit and then it comes back down. So why does the zeta potential decrease with increasing concentration of sulfuric acid? What a great question. Why does the zeta potential decrease? Say again?
Corrosion of the surface.
I don't know. I mean, I've added acid to the system, right? I'm adding sulfuric acid, okay, versus hydrochloric acid.
So strong acid.
Oh, good. It's still acid, right?
Could be that sulfate is doing something to.
Yes. And what is it doing? What's the charge on the particle surface? This is not a guess, right? You don't have to guess. Because you have, this is positive, this is negative, so the particle surface is positive. So you bring in a divalent sulfate ion that is a divalent counter ion to that surface charge. So what's happening is that the sulfate ion concentration is sufficient to compress the double layer. Good? Oh, what are you missing? Do not lose sight of this piece of information right here. This is 5 volume percent. Okay, so this is a dilute suspension. Good? We used a technique called electrophoretic mobility, and acoustophoretic mobility, excuse me, uses a sound wave that looks at oscillation and retardation of that. Don't worry about all that. The theory breaks down at 8%, but the literature that comes with the instrument says you can measure to 40. I don't know what the data means. We measured at 5, so we had sufficient signal, and we were within the theory. Okay, so we did nice data. The zeta potential data is repeatable. We're very happy about it. Okay. Now, this is the zeta potential data, correct? Okay. So if I look now at the viscosity data, okay, something else happens. So what you see first, here's HCl behavior, huge drop in viscosity. You can look at the math basically. If we look at the y-axis, we start about here. We're 1, 2, 3, 4, almost 5 orders of magnitude drop in viscosity with the change in pH. So it's a huge drop in viscosity. You would argue from something around sour cream to skim milk. Good? What happens on the base side? We would expect this curve to come down like this, right? We would expect a similar drop in viscosity on the base side of the isoelectric point, but that does not happen. The question is why? One question, so keep that one in mind. Here's the other. Connect the dots, unfortunate, but sulfuric acid, right? I'm able to efficiently drop the pH, but I see no decrease in the viscosity of the system. And again, the question is why? Why is it that the viscosity data does not match the zeta potential data? Or it does to a certain extent. but not completely. So what is it about this, okay, versus this? What is different? This is at 35 volume percent, right? So what does that mean? Oh, well, if I go back to this, this is at 5 volume percent, 35 volume percent. I have 7 times more surface area, you could argue, in this case than I do in the other case. That means that I'm going to have to add 7 times more acid or base to change that pH. So that means the concentration of counterions that comes in with that acid or base is going to be significantly higher, plus I have less water, right? So your dispersant, your changing pH operates against the surface of the particle, right? You're dissolving or you're corroding the surface of the particle, or you're coating the surface of the particle when you get to polyelectrolytes, okay? But ionic strength is based on the amount of liquid in the system, not the volume of powder, okay, or the surface area of powder. So ionic strength is based on the volume of liquid. We are at a higher concentration here. Therefore, any reactions that I have that have occurred on the surface of that particle now are going into less water. That means my concentration of ions in that bulk solution will be significantly greater in this case than it is in this case. Does that make sense? Okay, we see something else here. This viscosity, when I drop below pH of 2, my viscosity starts going back up rapidly. Why? Wait, let's look at the zeta potential data. Zeta potential data, well, it doesn't show that to happen, does it? It shows that mine, if I get down to pH 2, I'm at pH 2, so you'd argue it didn't quite show it here, but I'm not seeing a decrease in zeta potential data when I go to lower and lower pHs. And again, it's the same argument, right? I have a dilute system here, I change the pH. But here, my system is concentrated. Now, how much acid does it take to change my pH from 3 to 2? So it's not a trick question. What is pH? Say again.
The concentration of hydrogen.
Technically, yes, it is technically the activity, but close enough, right? So concentration of the hydronium ion, basically. So to go from a pH, and it's the log, right, of the concentration of hydronium ion. So to go from pH of 3 to pH of 2, I have to add in 10 times more acid. Wherever I was, I add another 10. And then I add another 10. So when I go from 5 to 4 to 3, I'm 10, 100, 1,000 increase in my concentration of acid. So what's happening is that I'm reacting this surface, but to go to the next pH level, I have to add a lot more acid. And I have those reaction sites on the surface. And so what's happening is that this increase in viscosity here is due to compression of the double layer, also by an increase in the chloride ion concentration associated with changing that pH to that level. If I were to go to lower pH, I would expect that to go up further. Okay? Sulfuric acid doesn't make any difference where I'm at. I have always exceeded the critical coagulation concentration with sulfuric acid because I have a divalent sulfate ion, okay, in this situation. And my drop in zeta potential here is because of that divalent sulfate ion. Okay? So I bring in sulfuric acid, I bring in a divalent counter ion, okay, that compresses the double layer. And it's even evidenced in the low volume concentration suspensions that make up the zeta potential data. Okay. These behave fine. So we are left to an inescapable conclusion that this shallow decrease in viscosity is due to the corrosion of the particle surface. Okay. Which means I'm putting aluminum 3+ ions in solution that are compressing the double layer. Okay. So this curve and this data and the zeta potential data and the viscosity data, they appear to be not entirely consistent, okay? But in fact, they are perfectly consistent and correct for the volume concentration of particles, okay? And you should become familiar with that. Good? Any questions? Do you feel that the exam reasonably represented what was talked about in class? Anything that you were really hoping to see that you didn't? Anything you wish you hadn't seen? Good. We'll go over the exam. You should know by now that some of these questions will show up again. Okay. If you have questions, go home, look over the exam, see what you got wrong or right. Okay. If you have questions about points taken off, you can come and talk to me about it. And I may ask you to come to class and ask the same question. Okay? Because I usually try to think of these questions in a different way, but I'm not probably thinking about the questions in the way that you are. Okay? So I take feedback on the wording of the questions, that's valid. All right? If you wish to argue for points, you may do so starting tomorrow. If you wait until December to do it, you're wasting my time and yours. Good? We'll go over your exams between now and Friday or whatever. And within the next week or so, if you wish to argue for points, you say that. Any questions? Yes.
I see there was a curve on the closed notes portion. What was considered each letter for the open notes?
Notes.
Okay.
So here's how I did it, all right? I added your score on the closed notes and the open notes together, okay? Subsequently, all right? And then I just did a simple grade. If you're at, if your points were over 100, you got an A. If they were from 80 on, you get a B, etc. That's what it was. But I only did it on the closed notes portion. Okay? Good. See you on Friday.
Yeah, exactly.
I might go for a little bit. Is what I always put aside?
That's very good. Yeah, that's not the speculating, she did really well. She was like, yeah, your interest are both probably either end. It's like, the bottom and
Yeah.
HP plus.
I was just anything with rebound, I was like, that's the guy.
Yeah, I'm glad that like I understood like how to invest in investment strategies.